Okay, for this last part, we're just going to lead up into some important ideas that we'll use a little bit later in chapter 14. So here's a theorem. We're not going to prove it. We are going to just believe it. But even believing it is hard, mainly because it's hard to just interpret what it's saying in the first place. So we've got this theorem, let f be a function of multiple input variables. Part A of this says that the maximum value of the directional derivative, the maximum possible value you can get, happens to be whatever the magnitude of the gradient is. The next part says, so it's still talking about, what the maximum value is, okay? Um, the first part is, what number is the maximum value? And then now that we know what the maximum value can be, when does it happen? That's what part B is trying to talk about. It happens when the vector u is in the same direction as the gradient vector itself. Now this, I want you to get a sense of what this is just actually trying to say. We're not going to try to prove it. We're going to just try to understand what it's saying. So part A tells us how large the value of the directional derivative can be. Part B tells us how to achieve this. Basically, how we achieve it is travel in the same direction as the gradient. So let's look at an example first, right? So we got the function f of x comma y equals x times e to the y at the point 2 comma 0. What direction do you need to travel in to have the value of f increase the most? So by part B, we need to travel. We need the u vector that we use for the directional derivative to be in the same direction as the gradient at the point 2 comma 0. So here's the gradient. Yeah, so the vector e to the y comma x e to the y. Let's now evaluate this at 2, 0. So replace every x with a 2, replace every y with a 0, and we'll get the vector 1 comma 2. All right, so there's the gradient at the point 2, 0. Okay, so at the point 2, 0, the gradient is the vector 1 comma 2. Now that vector, so we're standing at the point 2, 0 in the xy plane, and then we want the value of the directional derivative to increase as much as possible. That means we should travel in the direction 1 comma 2. That is, we should travel somewhat east, but more north than we travel east. That is, for every 1 unit traveled east, travel 2 units north. So it's like travel in the so from the point 2 comma 0, there is a line of slope 2 that, where did I get 2? Because change in y is 2, change in x is 1. So there's a line of slope 2, right? So that's steep ish, or steeper than a line of slope 1. And we should travel in that direction towards the northeast, or do I say something like the northeast? Okay, so starting at the point 2, 0, the value of the directional derivative would be biggest by traveling in the direction of 1 comma 2. Of course, 1 comma 2 itself isn't a unit vector, but we could normalize this vector. 1, 2 has length root 5. So the vector u that we want is 1 over root 5 comma 2 over root 5. That is trying to explain what this theorem is getting at. I think it deserves even more explanation though. So we just saw, given the function x e to the y, and we fixed ourselves at the point 2 comma 0. That's our starting location. The directional derivative is biggest by using u equals 1 over root 5 comma 2 over root 5. So what I'm trying to get at is, first let's look at our earlier computation, the vector 1, 2 is the value of, that is what the gradient is at the point 2 comma 0. So what I'm trying to say is this, and we'll actually just work through some computations using a computer. So if we did use exactly this vector that's suggested as the direction vector, the direction, what is the value of the directional derivative? Well, let's just take the gradient 1 comma 2, and we should dot that with this unit vector, and we'll get, in this case, 5 over root 5. I ran that through a calculator. You happen to get 2.24. The point I'm trying to make is that, or what is the theorem really trying to get at, is let's say you picked a different unit vector now. If you picked a different vector for u, not this 1 over root 5, 2 over root 5, but any other unit vector, that means that the value of the directional derivative at the point 2 comma 0 has to be smaller than 2.24. So for example, I picked the unit vector 3/5, 4/5, and I didn't actually do the computation, But if you took the vector 1, 2 and dot it with the vector 3/5, 4/5, which is how you'd get the value of the directional derivative, it has to be less than 2.24. If you took another unit vector and you computed the directional derivative, it's got to be less than 2.4. If you took the unit vector 8/17, comma 15/17, that also is a vector of length 1, and you compute the directional derivative using that for u, then you again have to get the directional derivative is less than 2.24, right? So what I'm saying is that no matter what unit vector you pick, this inequality here has to be true. So if you use the best possible unit vector to make the value of the directional derivative as big as possible, fine. Any other unit vector you'd use right here for the directional derivative, the number you'd get for the directional derivative value will end up being less than or equal to this value, which for this problem happened to be 2.24. I just computed the 2.24, which is certainly an approximation, just so that the three triangular points on this slide were a little clearer, right? I hope that it provided just a little more concreteness to actually have the number 2.24 on screen here. Let's take a look at a picture of some level sets. What we're going to do shortly when clicking on this is that in the app, it's just a quick Desmos thing, starting at the point 2, 0 to see the greatest change in z value. So per unit of travel in the plane, right? So all things equal, comparing apples to apples. To see the greatest change in z value, what you need to do is you need to travel in the direction of this unit vector 1 over root 5 comma 2 over root 5, right? And that's just the normalized version of the vector 1 comma 2. So let's go take a look at that. Okay, here we have the function f of x comma y equals x times e to the y. It's not shown directly here because it would be a three-dimensional graph. What you're seeing here is a contour map. That is, you're seeing several level sets. I'm not expecting you to ever draw the level sets for this function x times e to the y by hand, but I want you to know what level sets and a contour map are because that's how this explanation is going to make sense. So you see the level set corresponding to output 1 is in blue, level set corresponding to output 1.5 in green, level set corresponding to output 2 in purple, 2.5 in black, and 3 in red. And the point 2, 0 that was in the slide here, I have just asked the computer to draw. I happen to make the computer draw the point itself in purple because it was on the purple level curve. Now, the thing that the slide was trying to address was what direction, just doing one unit of travel anyway, should we go from this point 2, 0 to see the greatest possible increase in z value, right? And the point is, should we travel straight to the east? Should we travel up? Should we travel to the left? Should we travel down? Should we travel to the kind of southwest? Which way should we go? Well, look, if this is the level set with value 2, and in green you have just the level set of value 1.5, we certainly don't want to travel south or west or southwest. All of those directions are actually lowering the value of z. So those would be negative values of the directional derivative. We actually want to travel either up or to the right, or maybe from here somewhat to the northwest would work. But what is the best direction? I mean, what's the direction to increase the value as much as possible? We need to travel in the direction, as we saw, the unit, if we were looking for which unit vector, it should be 1 over root 5 comma 2 over root 5. So it's a vector that travels twice as far up as it does to the right. And we can actually just show this on screen. Sorry for how funky this looks, but among all the unit vectors which would lie on this dotted circle, we should travel this direction. And I hope that works for you, right? That from where we are here, traveling this way, you can see it would be along, along an arrow of length 1 that has its base point at 2, 0. This is how we could, as quickly as possible, have a unit length arrow that starts at 2, 0, touch the black curve as soon as possible. If we traveled purely to the right, for instance, you'll see that it takes a longer amount of time to travel along until we hit the black curve. So if we just put another quick interpretation on what's going on here, if we talk about, let's say, height, it's like x, y, maybe that's latitude, longitude, and we're on a hiking path, and this is a mountainous terrain. We want to find the steepest uh, place to go. And what we should do is to find the steepest thing, right? We don't want to take the easy path. The easy path would be to travel along the purple because that's all the same height. The height is 2 all along the purple path, right? So if we want the z coordinate to increase as much as possible, if our goal is to get to the peak of the mountain as quick as possible, we should travel in the direction of what the gradient told us, which is this direction here. Just as a quick note, we are going to skip talking about tangent planes of level surfaces. Um, let's take a look in the app we just saw. It is linked here again. To increase the z value as quickly as possible, uh, you should travel in the direction of the gradient vector, at least the unit vector version of that for you, right? That also happens to be perpendicular to the level curve. So let's take a look at that here, right? So if you look at this vector here, it turns out that that is orthogonal to this curve here, right? So if we could zoom in, let's just do it. This thing is perpendicular to that. It's kind of a curiosity that this occurs. There are other examples of this. So if you've hiked, you might actually sense this, that if you've ever used a topographic map, to increase the altitude as much as possible, you should travel perpendicular to the level curve. So somebody who wants to be, very, very easy going on their hike would say, oh, I don't want the height to change at all, so I'm going to just travel along a level curve. And then somebody who wants the height to increase as much as possible would need to travel in a perpendicular direction to that. So here's another example. I took a screenshot of a YouTube video of somebody playing Wii Golf. But if you play Wii Golf, take a look. Like, this kind of thing. Sometimes you're on the green and you get that map in Wii Golf that shows you various heights. And depending on where the hole is, you might need to increase the height as much as possible. If that hole is at the top of a hill, for instance, that's probably what you'd want. So to increase the height as much as possible, your goal is to actually hit the ball perpendicular to the level sets. And of course, the level sets are shown here with the slightly different shades of green. One more quick example here. Let's just consider, I took a screenshot of a website. This happened to be the US, showed the temperature on one particular day. It's just what I could find online. It was April 30th, 2016. And let's say that the Z coordinate here, let's just say represents height. So the z coordinate here, the z coordinate here represents temperature and xy represents latitude, longitude. And let's say you were in Oklahoma City, which I think is roughly where the line for 70 is labeled, right? So this black line separating the yellow and the orange is a level curve, right? All the places there have not a height, but have a temperature of 70. And if you wanted to get somewhere that was warmer as quick as possible, where do you go? You don't travel along the level curve. That means the temperature just remains 70 the whole time. What you want to do if you want things to be warmer is you need to travel perpendicular to here, at least in an instantaneous sense, perpendicular to this level curve. You should travel, well, what appears mostly to the southeast here, right? And that happens to be the gradient vector. You shouldn't travel along the level set. If you did that, you would just experience 70 degrees the entire time. Travel perpendicular to the level curve, and that perpendicular direction you travel actually happens to be the gradient vector itself.